Welcome back. Now we are going to look at this section where we will try to emulate all four processes rather quickly, because now you understand this is a simulation of ideal gas law in your VMDL lab, and we are starting with the additional parameters here. Let me bring them up, and let's make this full screen. And if you look at here, the number density is very low and it's all gas phase. So, we are starting with the gas phase, and so why don't we start with the isobaric situation, because that is what we wanted to do first, and then see how that works, because we have already done isothermal and isochoric models. So, what it requires that we provide a piston, because we are going to do isobaric, and then we will also change the temperature, and then we will see the variation in the work that will be supplied to the system, both PdV term, P delta V term, as well as the heat that we will be supplying it to take it from P1 to T1 to T2 temperatures. So, let us start with low density, which is fine, because we are looking at ideal gas situation, and there are two different molecule, two different atoms of different kinds, but because it is very small size, let me change the density. So that you can see the bigger size of the particles here, and these are ideal gas. So, you can think about these argon and krypton gas atoms that you are looking at in an ideal gas situation. So, let me start that. It is going to tell me that we change the parameters, which is okay. Now, you can see it nicely, that is good. So, in the parameters, it is rigid container, this is isochoric system. So, and if you look at, I have put a piston on top, and this is the constant pressure situation. So, let us look at this pressure. As you can see, it is constant around 2.0, fluctuating, but it is constant around the average value of 2.0. And then what we want to do, we want to give it a shot for a little while to reach rather equilibrium situation. But as you can see, it is low density, so it is all gaseous phase. Now, what we are going to do, pause it, then we are going to change the temperature, and now that we were at higher temperature, we are reducing, we are taking away the heat from the system. So, I am going down to from 3.99 to let us say 2.99, almost factor of 1 order of magnitude, and then we are going to run it. The piston is active. So, the pressure is gone down, with the temperature is going down as well. Before I do that, let me pause it, and because this is lock piston, so it is not moving, unlock it. So, now we are going to unlock that, and there is very small external pressure and mass is also very small. So, now let us look at that. Now, you can see clearly that the piston moves upwards, the volume of the container increases. At this point, the height of the container is exceeded screen limit. So, program will automatically reduce the magnification. So, you can see those magnifications. So, now you can see how with the temperature it is happening here. So, let me do one thing in order to rectify this situation. I am going to change the density a little bit more. So, now you can see that it is coming down with the temperature going down. So, now what you are seeing, this is isobaric situation. So, the piston can move up and down in order to keep the total pressure constant, and the pressure is fluctuating because kinetic energy distribution is fluctuating. And at certain point, this piston going up and down will change, and there is another way we can damp it by if I stop it here, pause it, and then increase the mass of the piston. That will allow me to damp these vibrations. So, let us do that. Now, you can see that it has less fluctuations, and that has become external pressure, and if you look at pressure versus time, it is constant. So, this is an isobaric situation. Now, in order for me to change the isotherm, what do we have to do? We have to change the temperature. So, we are going to further down, because we are at the limit of it, and we will observe the both the heat taken out as well as the constant pressure kept on the system. Now, again remember, you have to give it some time for it to come to the equilibrium situation. So, now we are coming to the equilibrium situation in isobaric, and as you know, it is going to fluctuate, which is a good demonstration that you should wait for the system to get to equilibrium situation. It will show some fluctuations. So, you need to take almost 10,000 time step first and not take any measurements, not take any calculations or data. And once it has come, and you can also observe by plotting these properties on various software that you have, see that the property has become a constant, and then you are going to, now if you look at, it is rather closer to constant. However, there are still fluctuations up and down. If they become acceptable level of error, now you can see, okay, create another isotherm. So, now I am going to create another isotherm by pausing it, and then they are changing it further down and see what happens to the system. Start it. So, what we should see from our understanding of the Charles law, that the temperature is related with the volume of the gas. So, as you reduce the volume, the temperature volume will also decrease. As you remember, Charles law has this linear relationship between volume and temperature. As you increase the temperature, volume increases. As you decrease the temperature, volume decreases. Okay. So, now we are gone again down to that. Let us do because we are in molecular dynamics, we can do anything. We have full control on the system. Now, what we are going to do, we can pause it and take it to extreme situation. And I am also going to increase the mass of the system and see what happens. And this is the fun. You are not breaking any jars, you are not breaking any equipment, you can do anything that you want. Now, see the artifact, and which is realistic to some sense, not in terms of the values, but in terms of the trends, is that the particles are moving slower because they are become heavier. And if you look at here, because we decrease the temperature, also you see crystallization. So, this is where you can see now we converted this entire gaseous phase to the solid phase, and it is not going to move much. So, even if I now increase pressure, let us try to increase the pressure on the system by pausing it here, and we are going to increase the pressure mass, external pressure, keep the mass same. I am going to increase the pressure and start it again. So, you saw this pressure line going up, which is very good for you to look at. And if you look at again, they are become very solid like, but the volume is not going down because it is occupied by the bonds now which are formed between these atoms, that is going at the atomic level. So, krypton and xenon, whatever the ideal gases are used here, they are essentially solidified. So, let me stop here with the molecular dynamics simulation and now do a summary of what we have learned today. So, we started with the understanding of the basic laws of thermodynamics. We looked at the 4 different laws of thermodynamics. Zeroth law, which says that the temperature of the two bodies when they are in contact will become same in the equilibrium. First law, where we said that the energy is conserved and it can convert from heat to work and work to heat. The third law, we also looked at the entropy, that the entropy always increases, the increasing entropy law, which is the Clausius statement. Then we also talked about, but we have not looked at that situation, which we can simulate in molecular dynamics, is that when we take a substance to 0 degrees Kelvin, absolute 0, does the entropy also becomes 0. And I think that is a very hard practical situation, but that is the third law of thermodynamics. After we understood that, we looked at various cyclic processes. We understood that we can do thermodynamics in 4 distinct processes: isothermal, isochoric, isobaric, as well as isentropic, which we will be talking in more detail in next sections. But in that case, we understood the gamma factor, which is a ratio between Cp over Cv. We also understood that there are 2 different kinds of specific heat. One is under constant pressure and one is under constant volume, and they are related with the Cp is equal to Cv, which is plus R, which is the universal gas constant. So, if you look at for ideal gas situation and for the ideal gases like argon, xenon, krypton, we have very good understanding, and we can do all kinds of thermodynamic experiments, and we can introduce different processes going from one pressure to another. We will also look at from VMDL simulations that we can keep the temperature constant, then we can keep the volume constant, and finally, we were also able to put a piston on top of the system ideal gas mixture, and then allow it to move back and forth to keep the pressure constant, creating an isobaric situation. And then we will also do some of the other more advanced simulations to understand isentropic. So, in conclusion, what I have to say that now you have good understanding of thermodynamic parameters, and we understand how to set up the system, what kind of processes are possible, what are the variables between temperature, pressure and volume, and how we are going to control them. And also very important thing that we talked about is entropy, and that is the order parameter. It sets from order to disorder. So, that is very important factor in terms of phase transition. Now, in the next section I am going to open with some of the free energies that you will calculate in terms of the internal energy, free energy, as well as we will talk about the Gibbs free energy and the Helmholtz free energy, and that will be what we call as thermodynamic potential. So, get ready for very exciting work that you are going to do with thermodynamic potential. Thank you.